So, good evening, everyone. In our last class, we have been discussing about the DFT and how we can implement the numericals. Okay. So, uh, today we will start with the fast Fourier transform. So, the fast Fourier transform, it is not a separate transform, but it is an algorithm by which we can implement DFT. Okay. So, usually, the fast Fourier transform they can be implemented in two ways. The first one is decimation in time, and the second is decimation in frequency. Okay, and this architecture, which is regarded as the butterfly architecture, it forms the basis of the fast Fourier transform. Okay, so if you look over here, so we are having two signal components A and B, and this is nothing but your Twiddle factor. Okay, so Twiddle factor is over here, and then there is crossover of signal components over here, and in the lower branch if you see there is a multiplication of -1. Okay, so what happens in the first terminal, we are having A plus B into WL. Okay, in the second terminal we are having A is going here, and then here. A, B, Wn multiplied by minus of 1. So it becomes minus of BWN. Okay. So in the top part we are having A plus BWN, and in the lower branch we will be having A minus BWN. Okay. So this butterfly architecture, this computation, it forms the basis of the fast Fourier transform. Okay. Now, what are the differences between the discrete Fourier transform and fast Fourier transform? Okay. So both of them, as I told you, the fast Fourier transform, it is basically an algorithm to implement DFT. So what then why we are calling it as fast Fourier transform? As the name suggests, the computational complexity of fast Fourier transform, it is lower than the DFT. Okay. So if you look into the definition, so definition is for the DFT a mathematical technique to convert time domain signals into frequency domain signals. Okay, that we have discussed in our last class. So FFT, it is an algorithm to compute the DFT efficiently so that there is a reduction in the computational complexity, right? So when we talk about the computational complexity, if you see over here, it is O of n square. That means there would be a quadratic increase in the computational behavior as the length of the n it is increased. Suppose the length of the signal is 10, it gets we get 10 square as 100. Now if the length of the signal it becomes 100, then it becomes 10,000. So if you see, there has been a quadratic increase in the computational speed as computational complexity as we increase the n value. Okay. On the other hand, if you look herein, we will be having n multiplied by log of n. So herein, what we will be having, we will be having a very less amount of computational complexity. Okay, so the execution time, it is slower as there would be higher computational complexity. On the other hand, FFT, it would be much faster. Algorithm, it directly computes the DFT using its definition. On the other hand, it uses algorithms like Pulley-Tucky algorithm to decompose DFT into smaller parts, and then we can perform the FFT. Okay. Memory requirement over here in DFT it would be higher. On the other hand, in FFT it would be lower. Application, it is useful for smaller data sets where computational efficiency is not critical. On the other hand, in the case of larger data set, FFT is preferred. Result accuracy, exact computation of DFT, provides the same result as DFT but computed more efficiently. Okay. Lastly, implementation, conceptually simple but computationally intensive. On the other hand, FFT, it is more complex to implement but highly optimized for performance. So over here, if you see O n square, it indicates that the time and space complexity of algorithm increases quadratically with the input size. If the input size doubles, the time or space required roughly increases by a factor of 4. Okay. On the other hand, O n into log n, it indicates that time or space complexity grows more than linearly but less than quadratically with respect to the input size. It should be this n. Specifically, it grows by a proportion of n multiplied by the logarithm of n. Okay. So difference in computational complexity between DFT and FFT. So most of the things I have already told you. Herein what happens, there would be n square of multiplications and n squares additions. So in our last class you have seen that when we are calculating DFT, we are basically doing a lot of multiplications and a lot of additions. So the number of multiplications are n square and the number of additions, they are also n square. Okay. So again, if you see in the case of FFT, we'll be having n into log n multiplications and n into log n additions. It would be required in the case of fast Fourier transform. Okay. Here also it would be log n, double n it has come by mistake. So if you look into example, so the example is, if you look, if there are 1024 data points, so it comes out to be 10,48,576 multiplications and additions would be required. On the other hand, in the case of FFT, we would be having only 10,240 operations. Okay, so you can see the number of computational complexity, it reduces drastically in FFT. Okay. So the DFT needs over a million operations, whereas FFT can compute the same result within just over 10,000 operations. This stark difference illustrates why FFT is preferred for practical applications, especially when dealing with large data sets. So then coming to the fast Fourier transform descriptive overview, most of the things has been discussed, and some of them what I will try to do is that I will try to discuss it through the numericals. Okay. Yeah, this is important. How the FFT works, it includes several steps. So that includes divide and conquer step. The algorithm splits the input signal into smaller parts and computes the DFT of these parts and then combines the results. Then recursive decomposition, the signal is divided into even and odd indexed elements recursively, applying the FFT until the size is reduced to 1. And lastly, combining the results from the smaller DFTs are combined to form the final result using properties of complex numbers to reduce the number of operations. This recursive approach, it drastically reduces the number of necessary multiplications and additions. So these are the applications of FFT in different field. Then over here, the application of FFT in biomedical signal processing in various fields, it has been given. So ECG analysis, then electroencephalogram analysis, heart rate variability analysis, respiratory signal analysis. Then in biomedical image processing, you are having MRI, CT imaging, ultrasound imaging, functional MRI, and OCT, optical coherence tomography. Okay. So if I give you a descriptive note to discuss about the applications of FFT in various biomedical engineering aspects, then you have to discuss about this biomedical signal processing and image processing techniques over there in detail. Okay. So anyone who does not know any of this thing? So MRI, I think every ECG, every one of you know encephalograms. These are basically the ECG signals. Heart rate variability. What are these? These are nothing but the signals of the RR intervals. Okay, we call it RR interval signals. So you know that in an ECG you are having signal like this, where these are the R peaks. So this is QR S complex. This is again another R peak. So the distance between these two R peaks, it is regarded as it is in time domain, right? So ECG signal, they are being acquired in the time domain. So the distance between two R peaks, it is regarded as RR interval. So whose unit is in time, right? Now, when you take this RR interval in the y-axis, RRI in the y-axis and time in the x-axis. So you will get some values which varies with time, and that is that signal what you obtained by plotting RRI versus time. It is regarded as the HRV signals. Okay, and through this RR interval analysis or the heart rate variability analysis, we can have an understanding about the autonomic nervous system of our human body. Okay. Similarly, respiratory signal analysis, we have the respiratory signal, we can perform this, use this FFT to detect some abnormalities and the breathing patterns and all these things. So coming to the biomedical image processing, MRI is the magnetic resonance imaging. CT imaging is the CT scan. What you go over there, we basically use the X-rays for getting the images. In MRIs, we basically use magnetic field, strong magnetic field to get the images. I'm not going into the details of that because we will be studying it in the next semester in medical imaging and image processing class. Then ultrasound imaging, we go for this abdominal scan for various reasons in both males and females. So over there we use ultrasound for imaging purposes. Then functional imaging, over here we have the functional MRI and PET scan, which helps us in understanding the functionality of certain part of the body. Okay. Then optical coherence tomography, it is similar to CT scan. However, over here the visible light is used and hence the term optical. So it allows us to image a specific part of the body and create 3D images of that specific part just by using optical or visible light. Okay. Then coming to the variants of FFT, there are basically four variants. First one is the radix 2 FFT, radix 4 FFT, split radix FFT, and real valued FFT. Among these, due to the constraint of time, we will mainly be discussing about the radix 2 so that you get an understanding how this FFT works. Okay. Then advantages of FFT, it is highly efficient, we can employ it for real-time processing, and it has got wide applicability or applications as we have just seen in the last couple of slides. Limitations, we can only use fixed input size, and the memory usage as we go for the large inputs, it may be quite high. Now coming to the FFT, so this butterfly architecture we have already discussed. Now suppose we are given with a signal xn, okay? So what do we mean by the this decimation process, okay? So in the decimation process we already discussed that we are basically recursively breaking down the signal. Recursively means continuously, okay, one after the other. In the first case, if you see, if we consider this as the signal, so what we have, we first take the odd components here. Okay, so we have taken it together. Then the even components, they are taken on the right hand side. Similarly, this was the first level of decimation. Next, again we will do the decimation for the odd and the even components. Okay. Now, for a for an 8-point FFT, so what will happen is that we will be using this sequence. We will be using this sequence as the input for DIT FFT. Okay, DIT FFT means decimation in time. So we have decimated the signal in the time domain, and after decimation, whatever the sequence we have got from top to bottom, we will be putting the values in that way. So what does that mean? So that means in place of a, we will be having x of 0, then we will be having in the next terminal x of 4, then we will be having x of 2, then we will be having x of 6, and so on. At the last, we are having x of 7. Okay, it would be in the input terminal. Okay, so in DIT FFT, what happens is that our input is in the decimated order and our output is in the normal order. Normal order means what is the input? Time domain signal. Output is the frequency domain signal. So our output would be in the order of x0, x1, x2 and so on to x of 7. Okay. So it will be in the normal order. Input is in the decimated order. Output is in the normal order. Did you get my point? Next comes what happens if we are doing DIF FFT. In DIF FFT, the output would be in the decimated order. The output will be in the decimated order and the input will be in the normal order. Okay. So DIT FFT, input is decimated order, output is normal order. In DIF FFT, input is normal order, output is decimated order. Okay. So this decimated order can also be determined by bit reversal method. So what does this mean? So we are having only up to x7. So we can represent 7 with a value of 3 bits. Okay. So LSB 0, 1, 2. So x0 it can be represented as least significant bit and most significant bit would be this thing. So x0 would be 0, 0, 0. 1 would be 0, 0, 1. 2 would be 1, 0, 0, 1, 0. 3 would be 0, 1, 1. 4 would be 1, 0, 0. Then 5 would be 1, 0, 1. 6 would be 1, 1, 0. And 7 would be 1, 1, 1. Now, what do you mean by bit reversal? So, the least significant bit, it would become the most significant bit, and the most significant bit would be the least significant bit. That means you are just reversing it. Okay, you are just reversing it. So, if you do that, if you see 0, 0, 0 will remain 0, 0, 0, 0, 0, 1, it would become 1, 0, 0 because 1 has come here, then this 0 it has come here, and the MSB it has come here. Then 0, 1, 0 it remains the same in both the cases. Then 0, 1, 1 it becomes 1, 1, 0. This one has come here, this one has come here, and this 0 it has come over there. Okay. So are you getting my point? So in this way, when we do the reversal and then when we come to the binary form, this decimal form, So what happens? We get the order of 0, 4, 2, 6, 1, 5, 3, 7. So if you go back, the same order was obtained over here also. Okay. So sometimes in some books you will find that the order is in the decimated form, and in some books you may find that the order of the signal is in the bit reverse form. Both of them, they are meaning the same thing. Okay. Now DIT FFT. So what happens in DIT FFT? In the first point, if you see, we are having two inputs, right? And our signal is x0, x1. So our capital X of 0, it would be x of 0, because this x of 0, it is directly coming over here, plus x of 1, W02, it is coming over here. Okay. So it comes out to be x0 plus x1. Right. Next, in the next terminal x1, it would be x0, we got, then x1 into W02 multiplied by -1. So this is 1 basically. So we get minus of x1. So in capital X of 0, it is x of 0 plus x1. Capital of x1, it is x0 minus of x1. Okay. Now coming to the 4-point DFT, what you have to do is that first, if there are 4 inputs, if you want to do the FFT for the 4-point signal, then initially you have to do 2-point DFT, and after combining these results, we have to go for the 4-point DFT. So how it is done? Let's see. So initially, what we discussed that the input should be in the decimated form. So we will arrange the signals in the decimated form. Then we will draw the lines over here, the signal paths, and then we will perform 2-point DFT. So we'll be clubbing x0 and x2, and we'll be clubbing x1 and x3 to perform the DFT. So over here we are doing 2-point DFT. So we get W02 as the twiddle factor. So at the top we are having the continuous line. At the bottom we are having the twiddle factor multiplied and multiplied by -1. Okay. Now what happens? The intermediate output would be A equals to x0 plus x2 as seen from here, and B would be x0 minus of x2. Similarly, over here if you combine these two, it would be x1 plus x3 and x1 minus x3. Are you getting my point? Now, next what happens? In the next stage, we have to perform 4-point DFT. We have to perform 4-point DFT. Now, when you are doing the 4-point DFT, we need all these ABCD components. Okay. Now, herein, if you look into the butterfly architecture, there were only 2 traces, and if you draw an imaginary line in between, so what was there? Beneath that imaginary line, we were having the twiddle factor, and above the imaginary line, we are having a multiplier of 1. There was nothing, that means there is a multiplier of 1. Okay. Similarly, when we are talking about this 4-point DFT, at the mid, we have to draw an imaginary line. And once you get this, so in the bottom part, what you have to do? You have to put the twiddle factor. How will you put the twiddle factor? Herein we are basically discussing about the 4-point DFT, and in the 4-point DFT we have W04, then the next line would be W14. Okay. Now if you see across this imaginary line, we are having, say, A. Below this imaginary line we will be having A dash. Then let us take it as B, and the bottom part it would be B dash. So what will happen? The signal component A will come to the A dash part, and the signal component from A dash, it would go to the A. Similarly, from B to B dash and B dash to B. Okay. And wherever we are having this total factor, there would be this multipliers. Okay. Now, if you look over here, capital X of 0, what is it? It is nothing but A plus C. This is the A. It is directly going over here. And this C, it is going over here. Why? W04 is 1. So A plus C, and over here, if you see, it is A minus C. Similarly, if you look into the B terminal, which will give you x1, it is B directly coming over here, B. Now over here, if you see, minus of JD, it is coming. Why this minus of JD is coming? This is coming because D is getting multiplied with W14. So W14 is 0, that means 1 minus J. So minus J multiplied by D. Okay, did you get my point? From where this minus sign minus J it came? Because W14, its value is minus of J. So that's why you are getting plus of minus J D, that means B minus JD, right? At the bottom part, B minus J is getting multiplied with minus 1, it is plus JD. Are you getting my point? So in this way we perform the 4-point DFT by the FFT method. Okay. So when we go for the 8-point FFT, so what happens? Initially we were having 2-point FFTs. Using these 2-point FFTs, we got the outputs were used for calculating 4-point DFTs. Okay. Now, from here, these 4-point values, they would be used for calculating the 8-point DFT. Okay. Over here, if you see, this is the imaginary line. At the below parts, we are having W08, W18, W28, W38. Okay. The total factor values you can calculate, and then the same way, if you consider it as say A, B, C, D, and here A dash, B dash, C dash, D dash. So from A to A dash is coming, and from A dash to A we are again connecting. Then B to B dash we are connecting, B dash to B we are connecting, and then again at the bottom parts we are having this minus 1 multipliers. Okay, so you can compute the W08, W18, W28 and W38 total factors, and you can implement the 8-point DFT. So over here what is happening? We are starting with smaller segments, and then using those smaller segments we are computing the larger segments, and recursively we are performing the fast Fourier transform so as to get towards the higher level. Okay, so herein what we have done, initially we have found out the DFT for small parts, so that is what we called as the divide and conquer rule. Okay, then recursive decomposition we did it for the input and output relationship to finding out, and then what we are doing, whatever the computations we are doing at smaller levels, we are combining all the results to get the final result. Are you getting my point? Now, for the sake of understanding what we have done, what I have done is that you will not get this in any of the books. So I have made a table. So there is, this is for an 8-point FFT. So you can implement it for the 4 point or 2 point FFT also. So if you want to do 2 point FFT, you just need to take this portion. Okay. If you want to do 4 point DFT, you just need to take up to stage 2. The rest all it is these are not needed. If you want to go for the 8 point DFT, then you need this full table. Yeah. So coming to the thing, so if you see in the stage 1, we are clubbing the signals in a pair. Okay. So if you see, I have clubbed the signals in a pair by marking them in different gray shades. So in the top part, there is a multiplier of 1. In stage 1, W02, the multiplier, it remains the 1. So these yellow highlighted regions, they are basically the Twiddle factor values. Okay, they are basically the Twiddle factor values. Okay, so if you see, if you take x0 as the a, so we get a dash equal to a plus b, and b dash we get a minus b. Okay. Similarly, we can compute c dash and d dash, c plus d, c minus d, then e dash, e plus f, f dash, e minus f, and so on. So now this output values, they will be taken to compute the 4 point FFT. So what is the middle value? The middle is this one. So beneath this one, what we are having? We are having the Twiddle factor values, and at the top we are having what we are having? We are having multipliers of 1. So this a dash, if you see a double dash, it is equal to a dash plus c dash, because first line to first line. Okay, here it is c dash equal to a dash minus c dash. Okay, now here b dash equal to b double dash, b dash minus jd dash. Here there is a mistake, it should be d double dash. So d double dash equal to b dash plus of jd. Similarly, in the second half you will be doing the same thing. Now after getting this output, we'll be doing the 8 point FFT. So this is the middle line. So beneath this middle line, all the Twiddle factors would be there. Okay. So a double dash, it will be a double dash plus of e double dash. Okay. And here, if you see, a double dash minus of e double dash. Okay. Similarly, if you see b double dash f plus f double dash, the Twiddle factor value, and here also b double dash minus f double dash, the Twiddle factor value, and so on. I hope you have understood what I was trying to convey to you guys, right? Any doubt? Any doubt? No? Okay. Uh-huh. Here or where? In table? Here? See, you have got this A, B, C, D, this thing. So I just renamed this C as D dash and this D as D dash. Yeah, B dash. Okay. So what is happening? From A to A dash, yeah, we are exchanging the signal component. Then D dash, yeah, this A dash to A, we are exchanging the signal component. In a butterfly, you just remember there are only two signal paths. You have to forget this signal part while the second components. So only we are left with this one and this one. Are you getting my point? Now, Here, after this imaginary line, total factor value, it always starts from, if it is a 4 point, W04, the next one will be W14. Okay. Now, when you compute the other two, you have to forget these two, and you will just be concentrating on this line and this line. So this is B and B dash. So signal component from B, it will come to B dash, and from B dash, it will go to B. Okay. So you just remember this basic thing. And here also we have done the same thing. If you see, A dash is coming from here. Okay. So A dash is also going here. Right. So we have forgot this part and this part. So now next thing, when you compute C double dash here to here and here to here. Did you get my point? Now when you have computed these two, B dash to this thing and see B dash J D dash, B dash J D dash. The negative signs you have to compute accordingly. You have to put in the values. Are you getting my point? Anyone else? Is it clear now? Okay, good. Now the thing is that while we discuss the DFT was x of k equals to total factor into x of n. Okay, and when we did and when we look into the IDFT, it was x of n equals to 1 by capital N multiplied by total factor conjugate multiplied by x of k. So if what is x of k? Frequency components, right? So I can give you any frequency component and I can ask you, you compute the xn values. So what you will do, though this is said that it is DIT-FFT, but our input is x of k. So input, what I said, input will always be in the decimated order. Even though we are using frequency component for the IDFT, but the input would be in the decimated order because the algorithm is DIT-FFT. Okay, because the algorithm is DIT-FFT. Okay, so next what comes? Next we have this conjugate values, total factor conjugate value. If you see, in the first stage there would be no change. In the second stage there are some values, so this is C minus j, it has become j and j has become this. So over here also minus j, it has become plus, and this was minus j, this has become plus. So we just put the conjugate values. Rest of the method remains the same. First you will be in the stage 1, you will be doing what? You will be doing 2-point DFT, stage 2 4-point DFT, stage 3 8-point DFT. But while calculating xn, we are having this 1 by n multiplier. So in IDFT, you have to also have this stage 4 where you will be multiplying it with 1 by 8 in an 8-point DFT or FFT. If it is a 4-point FFT, you will be dividing the values at the end of stage 2 with 4. Okay. Now let's take an example. We're discussing this at a later stage in the next class. I will not cover the DIF-50 today, otherwise it will get jumbled up. Please practice. You'll be having one day in between. Please practice. If you don't practice, you'll be getting jumbled up everything in your mind while you try to solve the problem. Okay. So the thing is that if you see, we are having the values xn equal to 0, 1, 2, 3. Decimated order would be 0, 2, then 1, 3. See, 0, 2, 1, 3. Total factors are 1, 1, minus 1, minus 1. So this comes 0 plus 2 equals to 2. And here we get 0, 2, minus 2. Similarly, we get these values. Okay. Again, we use this value, and total factor for 4-point DFT is DFT are 1 and minus j w1 4. So 1 and minus 4. So you then put the values, you get these things. Okay. So in this same order, you get this x values, xk values. Okay. On the other hand, if you want to do the inverse DFT, so this is the input values, this one, then this one, then this one. The same process we have applied. We have got some values, say it to be x dash n. We got this x dash n, then xn equals to 1 by 4 of this one. So we got this value, so it is nothing but this one. Okay. So I am showing both the things simultaneously because so that you can understand when we do DFT, we go to the frequency domain, and when we do IDFT, we come back to the original signal. Okay. In between, if we do some processing, then you will not get the original signal. Okay. You have to keep this in mind. You have to keep this in mind. So this is the thing. So yeah. Uh-huh. Yeah. So we will be discussing this at a later stage. So you take up the examples. Yesterday's example, we discussed about xn equals to 2. You perform the 2-point and 4-point DFT in the class, and in the assignment you will this weekend you will be getting the assignment. Over there you will be getting 8-point, some 8-point DFT and FFT numericals. Okay. So now you perform 2-point and 4-point DFT using the DIT FFT method of xn equals to 2, and again once you get to the frequency domain, you again perform the IDFT. Okay. Which one? This one? Let me check. Let me check. No, minus 2, minus of j, na? यहाँ पे माइनस है ना, -2 multiplied by minus j, so this becomes 2j plus of 2j. Which one? This one? नीचे? हाँ, -2 it came here, -2 it came here, then -2 minus j 2j minus of 1 minus of 2j. The simple thing is that if there was something wrong over here, the inverse would not have got me to the xn.